Hello lovelies, in this video the brilliant Charlotte is going to be taking you through Edexcel AS Maths Paper 1 Predictive Paper for 2023. Now this is quite a long video, so make sure you've got your pen and your paper ready, and you don't have to do the whole thing all at once. You can just drop a timestamp down below if you get halfway through to remind yourself later. What I want you to do is to watch this video, pause when the question comes up, have a go at it yourself, and then play what Charlotte worked through the answer and see where you went right, see where you went wrong, see how many marks you would have got and what you come out with at the end. This is a really low stress, low key way of revising, so if you make a mistake and get something wrong, don't worry about it, we've got you covered.
Hi there, this is Charlotte from Primrose Kitten, and today we're going to have a look at this AS level paper 1 pure mathematics side of the course. So really important here to give this a go. We've got 2 hours-ish to complete this paper and we have 100 marks available to get. So let's have a look at the questions and I will let you know how best to approach them if you feel stuck. I'll just give you lots of tips along the way. Okay, so this very first question, if we look at the question, we can identify that this is like a graphs and transformations topic. And they tell us that we have a graph, y equals f of x. Now they haven't given us a formula for this function, they've just drawn it instead. And we'll often see this. So we're told that point A has the coordinates 3, 2. So we might want to just label that on just so that we remember it, but you can see that they've sort of written on those coordinates on the graph anyway. And then they say to sketch the graph of y equals fx plus 3. So what we need to know for this is to know what the translation or transformation of fx plus a in brackets means. And that's going to be something from the textbook that you have learned. You've learnt that in class, and really we want to know that off by heart. So what this means is it is a translation by minus a in the x-axis. So whenever it is a plus or minus inside the brackets, we know we're dealing with the x-axis, moving left or right. But likewise, if it's plus a inside those brackets, then it's actually going to go backwards. It is going to go to the left instead of to the right. So in this case here, because we're looking at fx plus 3, what we will do is this is going to be a translation by minus 3 in the x-axis, which means that any significant x coordinates that we know here, we want to move them 3 to the left. So that is going to relate to this point, and this point. So this first point was at x equals 0. Now it is going to be at x is minus 3. This point here was at 3, and so now it's going to move minus 3 along and it ends up at 0. And this point here was at 6, so if you move that by minus 3 in the x, or to the left by 3, then we end up taking that to a coordinate of 3. So if we had to sketch this graph, what we would get is those 3 points would now be at minus 3, 0, and 3. And because this is a sketch, the key thing to include are just the coordinates. So because we have those coordinates there, we need to put them onto the graph when we have the transformation. It's not so much about the shape looking exactly the same or anything, it's just that those coordinates are good. So it doesn't have to be like a scale diagram, it just needs to be accurate general shape and the coordinates added on there. Perfect though. So let us have a look at the next one. So here we want to describe fully the transformation that maps the graph y equals f of x to y equals minus f of x. Now this here again is really just a fact recall thing. We need to understand what that means. And what this is it is a reflection. So whenever there's a negative, whether it's minus f of x or f of minus x, we know it's a reflection. And in this case, because it is here, we know it's going to affect the y coordinates because it's outside the brackets. It affects the y coordinates, which means that it is a reflection in the x-axis. So x-axis would be essentially like the mirror line. But that's good. So that one, not really any understanding, just a little bit of fact recall really that we need. Okay, question C. says to state the coordinates of point A after the transformation of 2f of x. So let's just quickly sketch out the original function again. So we know that we had 0, 0 here, then we had 3, 2, and then we had 6 as well, so 6, 0 here. And we know that A is this one here. Okay, so for this one, it comes back to knowing off by heart what this transformation means. So something of the form y equals a f of x. And we need to know that that is a stretch. Whenever you have a multiplied factor, we have a stretch. This one is going to be by a factor of a. Because it's outside of those brackets, it's going to affect the y-axis. So that means that when we have y equals 2f of x, it means we're stretching by a factor of 2 in the y-axis. So if we go over then to the one that is relevant, so a was 3, 2, what that will become when we apply this transformation of 2f of x is going to be 3, 4, because it is only affecting the y-axis and it is doubling the y-coordinates by that factor of 2. So then for D, we want to state the coordinates of point A after the transformation, y equals f of 2x. So this is just a follow-up really. If we had f of ax, again it's a multiplied factor, so we're going to stretch by a factor, but this time because it's inside the brackets, we're going to stretch it by a factor of 1 over a, and this time it's going to be in the x-axis. So when we have y equals f of 2x, that means it is a stretch of a half in the x-axis. So we're only going to affect there the x coordinates. So here we had that 3, 2 to begin with, but then we've applied this transformation of f2x, and that then becomes 3 over 2, 2. So that there would be our final answer for part D. So there we've got our answers for part C, which we would write 3, 4 because we doubled the y coordinate. So by 2. And whereas for D, when we had this different transformation of y equals f of 2x, that became 3 over 2, 2, because we have only affected there the x coordinates, and that was by a factor of a half. Good, good. Alright, so if for any reason you didn't recognise those transformation facts, then put them on a flashcard, because that's some of the very few things that we do need to know off by heart in maths. You know, most of it's a doing subject, but we do need to have some tools behind us to be able to do what we need to do. Okay, so question 2a, we want to write down the value of c, given that root 5 times 5 to the power of c equals 1/5. So what I would recommend we do here is to write everything in the form of something to the power of n. So things like root 5, we can rewrite as 5 to the power of a half. Now that is another fact we just need to know. Whereas 1/5, we could also rewrite that. That is a reciprocal, and reciprocals can be rewritten as negative powers. Okay, so 1/5, we can also rewrite that as a power. So if we think of it, it's a reciprocal, right? It's a bit like having 1/x, but instead this is 1/5. So if we're super careful and we just write it as 1/5 to the power of 1, just so it's really crystal clear to us what we're doing, then that will be rewritten as 5 to the power of -1. So now that we've tidied these bits up, we can put them all together a bit better. So let's now just rewrite the whole thing here as 5 to the half, which was the root 5, times by 5 to the c equals 5 to the -1. Now the really important thing to remember here is of course our index laws, okay? So our index laws tell us that when we times two powers together, we end up getting the sum of those powers, all right? Again, is another little fact that we really need to know. So if you don't know them, stick it on a flashcard. So we can use this rule here to combine that left-hand side, and we can then rewrite that as 5 to the power of 1/2 plus c equals 5 to the power of -1. Now using that then, we can say 1/2 plus c equals -1. And by just rearranging that now, so subtracting the half, we can get that final answer that c is equal to -1 minus a half minus 3 over 2. So that there is our final answer for part A. All right, so we're going to use similar tools to do part B. Part B is also all about indices, all right? So we're given here 8 to the power of 3a plus 1, and we're asked to write this in terms of 2 to the power of something, all right? So the first thing we need to know here is that 8 can be rewritten as 2 cubed. So if we just replace the 8 here, place that 8 with 2 cubed. And we're doing 2 cubed to the power of that 3a plus 1. What we want to use here is another tool from our index laws, and when we do the power of a power, we multiply those powers together. Okay, so what we have here is we do have the power of a power still, and so we want to multiply those powers together. So we're going to get 2 to the power of basically 3 times 3a plus 1. Which we can simplify out there. We can multiply out those brackets and we get 2 to the power of 9a plus 3. And if we go back to the question, we say that we wanted to rewrite 8 to the power of 3a plus 1 in the form 2b, 2 to the power of b. We've got that now, haven't we? 2 to the power of something. So we can say then that b is equal to that 9a plus 3. And then we're great, we're done. Okay, so let's try the next question then. So this question here comes up really quite commonly, surprisingly. And here we are told that we have an equation, a log equation, and we're looking at a student's attempts to solve it. And the student has made some mistakes. And what we need to do is to be able to go through this work and identify where the mistakes are. And we're told here that there are 2 errors made by the student, and we just want to briefly explain them. Okay, so what I would recommend doing here is just looking through the steps bit by bit and trying to spot where the mistakes have crept in. So if we look at this first step here, you can see fine, that's not even a step, they've just written out that line. But then the next one where they say they've done the subtraction law for logs, well, they kind of have. I can see that they have used the rule log a minus log b equals log a over b, but I can see they've done something incorrectly. Because with the standard rule here I have just written down, notice that there is no reference to there being any numbers in front of the logs. There's no possibility for there to be a constant in front of the logs. Actually, to use that subtraction rule, you need to have just a plain raw log something minus log something with no numbers in front. So here in this question you can see you do have 3 log base 3x. And so that fact means that we can't straight up use the subtraction rule like they have in this case. We would beforehand need to use the log power rule, which states that if we have, say, k log x, we can rewrite that as log x to the power of k. So what we could say here is that the first little mistake is that the 3 log base 3 of x must be changed to log base 3x cubed before we use the subtraction rule. Okay, good. Right, so obviously that has already made a mistake, so there's going to be some follow-on flaws in the subsequent bits, but we're looking for a brand new, completely unique mistake that they have made for the second mistake. So they did some simplifying here. That looks fine. They've just used the power rules. Essentially x over root x, that is the same as x to the 1 over x to the half, and that is indeed x to the half or root x, so that bit there is fine. That simplification was fine. But then if we look at the next line where they use the power rule for logs, I can see a mistake there, because if we were to use that, we would have 3 log base 3 of x to the half equals 5. And there I can see that if I was using the log power rule, I would multiply through by a factor of a half, and I would get 3 over 2 log base 3 of x equals 5. And that there I can see is not quite the same, is it? So that's another potential mistake. Another one we could say actually is in that final step, you can see that we go from having log base 3 of x equals 5, and we've tried to get rid of that log base 3. The way that they've done that is 5 to the power of 3, but no, what that should be instead is that x equals 3 to the power of 5. So that should end up with 243 for that line, rather than x equals 5 cubed plus 125. But of course, there's been so many mistakes that have already happened in this that not to worry. But that's another one you could say, so it should be x equals 3 to the 5. Which equals 243 for that final line. Or you could mention the other one, the one where the power law has gone awry as well. Perfect. So for part B here, we want to find the correct solution to this. So we want to do this actually properly, all right? So first things first here, I would deal with this because we do want to use the subtraction rule, but to use the subtraction rule, remember we do not want any numbers in the front of our logs. So I'm going to rewrite that as log base 3 of x cubed minus log base 3 of, and we'll say x to the half now in place of root x2, just because that is good form to do that. So now I can use the subtraction rule because it is just in the form that we have here of log a minus log b. So that is going to simplify to give us log base 3 of x cubed over x to the half equals 5. And I can simplify that by just using the index laws that we know about. So we are familiar with the fact that x to the m over x to the n equals x to the m minus n is one of our special laws that we learnt back at GCSE and we still use all the time now. So that leaves us with log base 3 of x to the 5 over 2 equals 5, all right? So now that we have got that, what we can do is get rid of the log base 3. So what we would need to do that is do 3 to the power of each side. Now by doing that, we will get rid of the log base 3 and we're left just with x to the power of 5 over 2 equals 3 to the power of 5, which is 243. And then once we have that factor, we know that x to the power of 5 over 2 equals 243. We can now get the x on its own. So we could do this in 2 steps to get the x on its own, or you could do it in one big step. Of course, you need to think, how do you get rid of to the power of 5 over 2? So one way you could do it is you could first square both sides, and that leaves you with x to the power of 5 equals, and I need to double check what this gives us here, 59,049. And then to get the x then on its own, we just want to do the 5th root of each side. So if we do the 5th root of that, we simply get 9, okay? There's other slightly different ways you might have done that in slightly different orders, but so long as you get that same outcome, that x is equal to 9, then we know that we have done a good job there and we are happy. All right, so we just want to be really structured with that. We need to know our log rules off by heart. We need to know that before we use the subtraction rule, we need to make sure that there's no numbers in the front of any of those logs. And if there is, then you need to use the power rule for those, and then we should be good. But that's good. Let's try the next question. Okay, so this one here is now the coordinate geometry topic. And we're told that we have line A, we're told its equation, and then we're told that line B passes through 2 points. And we're asked to describe the relationship between A and B. Now for me, whenever I'm asked to describe relationship between 2 lines, I think, what could I even know about these lines? In all likelihood, we're going to be referring to their gradients, because that's really the only big property that we come to know about straight lines. So if we wanted to determine the gradient of each of these 2 things, what we could do is for line A, we can try and rewrite the equation in the form of y equals mx plus c, because by doing that we know that the number next to the x is the gradient, don't we? So then we'd have that fact about it that we can use in this question. So at the minute we have 6x minus 2y plus 20 equals 0, and let's work to get the y on its own. So we could shift the 2y on the other side, and we're left then with a positive 2y now, and we get 2y equals 6x plus 20. Then to get the y literally on its own without any factors or anything, we will then divide through by 2. So dividing both sides here by 2, we're going to get y equals 3x plus 10. So by doing that, we know that the gradient of A is 3. Okay? Then for line B, we're not given a line, but we are given 2 coordinates. And we know how to find the gradient of 2 coordinates. The gradient of 2 points is the change in the y coordinates divided by the change in the x coordinates. So in this case here, we're going to do the y coordinates subtracted from each other, and then we're going to do the x coordinates subtracted from each other. And then we will end up getting 4 over minus 12, which simplifies there to give us minus 1/3. Okay, so now we know that the gradient of line B is minus 1/3. So now we need to use our knowledge of gradients to be able to state if there is a relationship between them, and if so, what it is. So a certain fact about perpendicular lines is that the gradient of a perpendicular line is equal to the negative reciprocal of the other gradient. So here we could say that the gradient of B is equal to minus 1 over the gradient of A. And we can see that, can't we? Because of what we said. We said that the gradient of B is minus 1/3 and the gradient of A is 3, which means that they are equal to the negative reciprocal of each other. So for that reason there, we can say that the 2 lines are perpendicular. So to get all of your full marks there, you would first want to work out the gradient of line A, then we will want to work out the gradient of line B, and then we would want to express that relationship between reciprocals, and then we would finally make a little conclusion that the 2 of them are perpendicular because the gradient of one is equal to the negative reciprocal of the other. But that's good work. All right, so trying the next question here. The triangle ABC is such that AC equals 9, AB equals 16, and ABC is 25 degrees. So to be able to do this, we do really need to draw a diagram. I would not try and do this without a nice little diagram. So we've got a triangle ABC. We're told that the angle ABC, so this one, is 25 degrees. We're told that A to C is 9 centimetres and A to B is 16 centimetres. And we're asked to find 2 possible values for the area of the triangle here. Okay, so to do this, to find the area of a triangle, we know a certain fact. We have an equation. We have half AB sin C is our general equation for the triangle area. So to do this though, is we will need to know an angle on 2 sides, but we don't have the right angle on 2 sides. The angle that we have needs to be enclosed by the 2 sides we know. So potentially that means we would need to know what, say, this angle here is to be able to do that, to use it with the 16 and the 9. So to do this here, we would have to use another tool that we have to work out another angle so that we can work out that angle of BAC that I've labelled there. So for me, if in this question I would look at it, I would see that we have 2 sides, we have one angle and we want another angle. So in total here, we are going to want to leave up with 2 sides and 2 angles. And I know from GCSE that whenever there are 2 sides and 2 angles involved, I know that that means I use the sine rule. And I know the sine rule states that sine A over A is sine B over B, which is sine C over C. So let's use a different colour pen here and just sort of label this out then. So we've got angle B and we've got side B. We've also got side C and we don't know angle C, but then we don't know side A either, do we? So what I would do here is I would try to work out what angle C is, and then once we know angle C, we can then work out what angle A is, just by using the fact that the angles in a triangle add up to make 180 degrees. So let's do that then. So we could say that we know, let's just highlight out the things we know. We know B, we know side C, and we're going to find what angle C is. So let's substitute those in to get what we get. So we're going to have sine 25 over 9 equals sine C over 16. So sine C equals 16 sine 25 over 9. So using our calculator there, we can work out the number that we need. So we'll do inverse sine of 16 sin 25 over 9. And I make that there, the C is equal to 48.7050 degrees. Now, one thing to notice here, and one thing to remember now that we're at A level, is that there's often more than one value for an angle when we do inverse sine or inverse cos or inverse tan. Our calculator gives us one value, but we've now learned in A level maths that actually there's more to it than that. And that is heavily suggested in this question when we look at it and it says find two possible values. Find two possible values for the area of the triangle. Now, the only way we could possibly get two possible values for the area is by using two possible angles. So, with sine, we know that to find the other possible angles, we can do 180 minus the current angles to get the extra ones. And there's a lot of different methods to do it. You can use the symmetry of the sine graph, or you can use the cast diagram. But we can get another angle for C, which would be equal to 131.2950 degrees. So let's highlight these angles, our two possible angles for C that we have. So once we know what angle C is, we can work out what angle A is, all right? So angle A is going to be 180 minus 25 and minus that C, all right? So we're going to have two possible versions of that angle A. So we could say that angle A could be equal to 180 minus 25 minus the 48.7050. And in that case, that ends up leaving us with 106.2950 degrees. Or angle A could also equal 180 minus 25 minus 131.2950. And that ends up giving us an angle, another possible angle for A, equal to 23.7050 degrees. So let's highlight those again so that we don't lose track of them. All right, so the sine rule has been used here to work out the extra angle, and then we use the angles in a triangle adding up to 180 to get the angle that we need for this question. So now we want to work out the area. And like I mentioned, the generic equation for area that we've learned is a half AB sin C. Now that's great. The one reason why I'm just going to pause here for a minute and just explain something is, and it's the same case for the sine rule and the cosine rule, is those letters A, B and C are interchangeable, okay? One diagram and how it's labelled may not tally with area equals a half AB sin C. It just might not. In this case, it's not going to. So sometimes we might need to rejumble those letters up to fix it in a way that suits us. So here, the main thing to remember is when we're working out the area of a triangle is so long as we have an angle and the two sides surrounding it, that is what we need to get the area of a triangle. So in this particular case, if we use the lettering that we've been given in this question, the sine rule would actually end up giving us that the area equals a half BC sine A. But notice in both the first one that I wrote up here and this different variation, they mean the same thing. Notice that all three letters are present. So that's the main thing to notice there. You just want an angle enclosed by two sides, and then you can do the sine rule. So there, here we end up getting the area equals a half times 9 times 16 times by sine, and then it's the angle. So That could be 106.2950, or we could write it as the area equals a half times 9 times 16 sine of the 23.7050. So you will end up there getting your two possible answers for the area. It is either going to be 69.11 centimetres squared, or it will be 28.95 centimetres squared. So a big question there. I think lots of potential places for confusion, but so long as you're firm in this question, you just use whatever methods you can as you go through it and you're patient with it, then you will still get a good chunk of marks. Even if you're not quite sure how to finish a question, still do the bits that you do know how to do, because you will end up getting marks for them. Right, let's have a look at this question here. So straight away, by seeing that they want us to write it in this specific form, in this form which states that we want a brackets x plus b squared plus c, I know that that is almost like maths code telling us to complete the square. So whenever they write something in that way, then what we want to do is just recognise that that's code speak for complete the square. All right, so next thing to look at here is this is a slightly trickier complete the square question because of the fact that we don't just have x squared, we have 2x squared. And that really does change things, you know. So what I recommend with these cases is you will just kind of isolate the x squared and the x terms. And what I would recommend you do with those for now is factorize out that factor of 2, because then by doing this we can force it now to look like the basic version that we know how to do. So we're going to take out that factor of 2, and then that leaves you there with x squared minus 3 over 2x. And then we can just plonk the k on the end. That's fine. So now we get to the actual bit which involves completing the square. Okay, so I'm going to shade in this little bit here because this is the bit with which we need to complete the square of. So what we do when we complete the square is instead of writing x squared, we write x, and then we halve whatever the x value is. So at the minute it's minus 3 over 2x. We halve that coefficient, so we want to halve minus 3 over 2. And by doing that we get minus 3 over 4, and then we put a little squared here, and then we subtract whatever that value is here. We subtract the square of that. So what we've got here is that green region, the x squared minus 3 over 2x, can be rewritten as x minus 3 over 4 squared, and then minus 3 over 4 squared. So let's simplify this out then. So we've got x minus 3 over 4 squared, and that would be minus 9 over 16, because minus 3 over 4 squared becomes positive 9 over 16. So that is, in a simplified version, what that becomes there. But now we need to remember that there was 2 times that, wasn't there? And then at the end of it, we added k. All right, so what we want to do now is to multiply out the brackets on that, and we're going to get 2x minus 3 over 4 squared, and then minus 2 times 9 over 16 gives us 9 over 8, and then we've got that plus k on the end. So now if we want to say what the c is in the original equation, c is going to be this constant that we have here. So we could say that c is equal to minus 9 over 8 plus k. Or you could write that in the other way and write it as k minus 9 over 8. But that there is your answer, okay? So in part B, we're told to find the values of k for which the curve y equals 2x squared minus 3x plus k does not intersect the line y equals 1. So to do this, we're being asked to find where it does not intersect that line. So to do this, what I think is really beneficial is to use the fact we completed the square to provide us with a minimum point of that graph. So hopefully you remember that one of the most powerful things about completing the square is that it provides you with the minimum or the maximum point of that graph, okay? So here, from looking at our completed the square version, I know that the minimum value of y is going to occur when x is equal to 3 over 4. Okay, and the reason why I know that is because if I substituted in x is 3 over 4 into that equation, then I know that that big chunk becomes 0, and therefore the smallest possible value of y is provided, and that would be equal to just this region here. That's all that you would have left, 0 minus 9 over 8 plus k. All right, of a more standard format, if we had y equals x plus b squared plus c, then in that case the minimum would be at minus b, c, for instance, okay? So in this case here, our minimum value occurs when x is 3 over 4 and when y is equal to minus 9 over 8 plus k. Now you might be thinking, well, why is that important? And the reason why that's important is because we're saying find the values in which that curve, so the curve that we have here and that we're talking about, does not intersect the line y equals 1. Okay, so let's imagine what that looks like then. The line y equals 1, it could be cut here, it could be cut here, it could be cut here, or it could be cut here. Now those last two lines that I drew, they intersect the line, don't they? They intersect the curve. So in this case here, it intersects twice. In this case here, it intersects once. But all those points below do not intersect. So we have a little tipping point here, don't we? Where whether or not it intersects, it depends on what the y coordinate of that minimum point is. We know that in this case, the tipping point is when y equals 1, because we're looking at whether or not it will intersect the line y equals 1. So if that minimum point on the graph, this minimum point here, is at a point bigger than 1, so if that minus 9 over 8 plus k was at a bigger coordinate than that line of 1, then that means that it will not intersect. If it was equal, so if that minus 9 over 8 plus k was equal to 1, then we would say it intersects just the once. Whereas if it was less than, and then the curve actually fell lower than the 1, then it would intersect it twice, okay? Do you see why that relates? So we're saying that it must be bigger than 1 because it must physically be higher in the y coordinate than 1. Because remember, that is what this is. This is the y coordinate of this graph. So now that we know that, we can simply rearrange this to get k as the subject. So adding 9/8 to both sides, we get that k is bigger than 17 over 8. Perfect. So that one I think was quite tricky because it really expected us to understand the meaning of the graph, of the minimum point of it, and whether or not it's going to cross that horizontal line of y equals 1 or not, and what will relate to that. But let's have a look at the next question. Alright, so this question here is a great binomial expansion question. So to be able to answer this, what we want to do is to know this relationship here. So we know if we have something of the form a plus b to the power of n, we can rewrite, and we're looking at the first 3 terms here, so we'll just bother with those. We can write it as n0, a to the n, b to the 0, plus n1, a to the n, b to the 1, plus n2, a to the n minus 2, b squared. Okay, so I've just stated that, I haven't explained it. That's what I'm going to do now. But this is something that we do want to know, and the more that it's just in our memory, the quicker we'll get at it. So if we compare to what we're given here, what I would recommend that we do is to basically lay out what a is. So we're going to stick in a little a equals. So we're going to say a in this case would equal 1 because that is the direct comparison. What b is, which in this case is minus 4x, which is really important that we spot that. And also what n is. So in this particular case, you can see that n is equal to 7. So we can write here that n equals 7. So now that we've got all that information down, what we can do is we can go to this equation and insert them for those first three terms. So we've got 7, 0, a to the 1, which we know what a is going to be 1 to the power of 7, 1 to the power of 7, and then minus 4x to the power of 0, and then plus 7, 1, and then a to the power, well, we know what a is, 1 to the power of 6, and then times by minus 4x to the power of 1, and then finally plus 7, 2, and then that is a, or in this case, that is 1 to the power of 5, and then minus 4x squared. Okay, so it's really important to write down all of those steps because it's very easy to make mistakes along the way. Now this bracket notation, this 7, 0 bracket notation, what that will be when you type that into the calculator is 7C0, okay? And we can find that on our calculator. I know on my particular calculator that is just above the divide button, so I would press shift and then the divide button, and then that will give me the ability to use that. So if I was wanting to enter this in my calculator, my particular calculator, I would type in 7 and then I would press shift and then I would press the divide button because that has above it a little NCR, and then I would press the 0 button, okay? So that is the string of information that I would use to get that, and it would end up giving me an answer of 1 when I press equals, all right? So by putting that all in, we will get 1 times by 1 to the 7 times by minus 4 to the power of x to the 0, and then plus, and then when we do the 7c1, we just get 7 times 1 to the 6 times minus 4x to the 1, and then plus 7c2, which gives us 21, times 1 to the 6 times minus 4x squared. Now, where people will make mistakes here, we need to remember that anything to the power of 0 just becomes a 1. So that minus 4x to the power of 0 just becomes 1. And then here as well, minus 4x to the power of 1 will just become minus 4x. But here, this is another place where people make mistakes. So if you find yourself consistently making mistakes in binomial expansion questions, it may be things like this. So it's minus 4x squared. Now that means we need to square the minus, the 4, and the x. Okay, so that becomes plus 16x squared. Okay, so when we put that all together now, we will end up with just 1 from doing the 1 times the 1 times the 1. And then we will get plus minus 28x. So that there is coming from 7 times 1 times by minus 4x. And then finally, the final term is going to be plus 336x squared. And the reason for that is you've got 21 times by 1 times by 16x squared. And that there gives us our final term there. So our final answer for that binomial expansion is 1 minus 28x plus 336x squared. And the main thing there is just make sure you know the binomial expansion. Make sure that you know to write down the accurate substitution, including negatives, including any other things that might be there. You need all of that information in to be able to do this. And then make sure you know how to use the buttons on your calculator to get things like the NCR button working. That's good. So let's try out part B. So this is saying, without a calculator, evaluate 0.996 to the power of 7 using what we just worked out, basically. So to do this, what I would recommend doing is comparing our 1 minus 4x to the power of 7 to 0.996 to the power of 7. So by looking at those, we can see that the 1 minus 4x simply must be equal to the 0.996. So what we can do there is a little bit of a rearrangement to work out what x must equal. And so if we rearrange that, we'll get 4x equals 1 minus 0.996. So 4x equals 0.004, and then so x would be equal to 0.001. Okay, so that's our first mark in that question, by recognising that if we substitute x is 0.001 into our solution from part A, we will be able to solve this. And they want it correct to 4 decimal places. So we can do this without a calculator, to be perfectly honest, so long as you show every step of your working here. I don't think they're necessarily going to be able to tell if you've used a calculator, but just make sure that you're very heavily showing your working. The main thing they're saying by not using a calculator is they just don't want you just to type in 0.996 to the power of 7 into your calculator and then writing down the answer. They want to see this method. But full disclosure, I'm sure that I would be picking up a calculator for some of these next steps, but maybe just breaking it down a little more. So I'll show you what I mean. So we do 1 minus 28 times the 0.001 plus 336 times 0.001 squared. So all I've done there is everywhere where there was an x, I've replaced it with 0.001. And this is the bit where, as far as I'm concerned, even on the mark scheme, they're not going to be able to tell if you've used a calculator, so long as you do not type in 0.996 to the power of 7 into the calculator and you just type in what we've written down here, you will be fine, okay? Of course, you can multiply 28 by 0.001. If you feel happy doing that, then please do. But you will end up here with a final answer, whichever way you do it, of 0.972336. I think at the very least it would be helpful to use your calculator as a backup. A lot of my students say to me, oh, it's okay when you're here because you're there to ask those critical questions, but you can ask yourself them, and you can use your calculator as a little bit of a backup tool. That can be the checker, that can be the person in the room with you. If your calculator gets a certain answer, you can check what you have got yourself and see if they tally, and then that can be a good checker to see if you got it right or not, or if you need to go back to square one. That's good. So that there would be your estimate for that 0.9967 without using a calculator, or at least not directly entering 0.996 to the power of 7 into that calculator. Perfect. Let's try the next question. So this question here is all about a circle, and we're given its equation. Now, to be able to do this question, what we need to do is we need to know what the general equation of a circle is. So what that looks like is x minus a squared plus y minus b squared equals r squared. And in that case, AB would give you the coordinates of the centre of the circle, and r would, of course, be the radius. So here where we're asked to find the coordinates of the centre of C and the radius of C, what that is actually asking us to do is to rewrite this in the format of x minus a squared plus y minus b squared equals r squared. So to do that, what we want to do is complete the square, all right? So what I would recommend doing is grouping together all the x terms together and completing the square of those, and then grouping together the y terms and likewise completing the square of those, and then grouping it all together, simplifying it, tidying it up, and then you're done. Okay, so if we first take a look at the x terms, completing the square of that would mean you halve the 8, so we would get x minus 4 squared because we halve the coefficient of the x value. And then we subtract that value we just found, that halved value, so 4, we subtract the square of that. So we're going to subtract 16 because that is 4 squared. So then we're going to do the same thing now with the y's. So just to highlight those, just to make them pop. So we've got y squared plus 12y. So we're going to do the same thing. We are going to halve the 12. So we're going to have y plus 6 squared. And then we subtract now that 6 squared. So we're going to subtract 36. And then we've got plus 16, which came from the original equation that they gave us. And I just plonked that on the end there. Okay, equals 0. So now we've pretty much got it in this format that we want. So what I would do now is I would take all of these values that don't have any like x's or y's in them and simply move them onto the other side so that we can compare them to this r squared. So that ends up leaving us with x minus 4 squared plus y plus 6 squared equals 36. So that we can now directly compare to the original equation that I gave there right at the top of the page, And we can see the centre of the circle is going to be given by 4 minus 6 as our centre. And the radius, we can use the fact that r squared equals 36, and therefore r equals 6. And then we have got there the things that we needed for this question, and we're done. So part B follows on from this, and we're told that if we have that circle, the one we just talked about, and we also have the line with equation y equals kx, where k is a constant, we're told that it cuts at 2 distinct points. So that means that this line has 2 points of intersection with the circle. And we're asked to find the range of values of k for which that would be true. So to do this, there's one key word here that really jumps out at me that straight away tells me what I'm going to need to do in this question. And that there is the word distinct. I would go as far to say that the only time that you're going to see the word distinct come up is in a question where they want us to do the discriminant. So the discriminant, just to remind you, is given by b squared minus 4ac. And that gives us information about the amount of points of intersection or roots something has. So here we're told that there are 2 distinct points. So in that case, we're going to use the fact that this discriminant, the b squared minus 4ac, is positive, so it's bigger than 0. So now that we know where we're going to go with the question, we need to think, well, what are we going to work out the discriminant of? And because here we have 2 different equations, so we've got the equation of the circle and the equation of this line, it's not just a case of, oh, where does it cross the x-axis or something? What we need to do instead is to combine these, okay? So we're going to substitute one into the other to get a combined equation that we will then find the discriminant of. So the easiest way to do that is obviously we know that y equals kx. So how about we substitute that into our original circle equation? So everywhere where we see y, we now replace it with kx. So if we do that, y squared would be kx squared minus 8x plus 12kx plus 16 equals 0. And squaring that kx, don't forget we need to square both the k and the x. So we get k squared x squared minus 8x plus 12kx plus 16 equals 0. So looking at this, you might think, okay, I need to do the discriminant now. What is my A? What is my B? What is my C? And you might look at this at first glance and not be clear. What I would advise you to do is to factorise for the x squared, factorise for the x, and then your bracket will be your coefficient of x squared and of x. So that's going to be like your A and your B. So let's factorise them. So we will get 1 plus k squared, x squared, and then plus 12k minus 8x plus 16 equals 0. So if we are thinking back there to the discriminant, we could say then that A in that case is 1 plus k squared, B would be 12k minus 8, and our C would be 16. So now what we want to do is to substitute these values into our discriminant. So instead of b squared, we're going to do 12k minus 8 squared, and then we're going to do minus 4 times a, which is 1 plus k squared, and then times by 16. And we know that's bigger than 0. So we've just substituted the values into the discriminant that we said. Now we want to multiply out all the brackets and simplify. My one little top tip here really is going to be when it says 12k minus 8 squared, don't forget that is actually 12k minus 8 times 12k minus 8. It's double brackets. Very easy with this to just square each number, but nope, that is not what it means, okay? So let's work this out. So I make this 144k squared, and then minus 96k, minus 96k, plus 64, and that would be the brackets done. That first set of brackets, the 12k minus 8 squared bracket. And then I'm going to move on to the next bit. And so minus 4 times 1 plus k squared times 16. That leaves me with minus 64 and then minus 64k squared. And that is altogether bigger than 0. Alright, so now that I have done that in its entirety, I would now go through this and just highlight the k squared terms and highlight the k terms, and basically any other like terms I would just group together and highlight. and then I would simplify this. Okay, so I'm going to group together all of those k squared terms, and that leaves me with 80k squared. And then I get minus 192k. And then plus 64 minus 64 just cancels out, so I get bigger than 0. So now what I want to do is factorize this to solve it. Now, here I would always recommend almost pausing for a minute and imagining it was equal to 0 to be able to get those critical values or those solutions for k. We will then, once we've got those critical values, work out what range of values it's going to be bigger than 0, okay? So I would sort of recommend suspending reality just for a moment and putting it equal to 0 to get those critical values. I would factorize this out, so I'd go k. You could take out a bigger factor than that as well, maybe like a common factor between the 80 and the minus 192, but you will still get the same outcome. So here the solutions for k, the critical values, will be k is equal to 0 and k is equal to 12 over 5. So now that we've got those critical values, what we want to do is do a little sketch. Now I always recommend this. This sketch does not need to be to scale, it just needs to be the right shape and the right direction. So because this is a quadratic equation and a positive quadratic equation, I would do my little sketch, something like this. I would label on my values. So I've got the values of the roots, which are of course what k are giving us in this case when we imagined it was equal to 0, because 0 was this line here, that horizontal line where y equals 0. And then now we'll think, all right, so we are looking at when it is bigger than 0. And like I said, if you imagine that that horizontal line of the x-axis is when y is equal to 0, well then when is that y-axis bigger than 0? When does the curve go into positive values of y? And so if I shade those regions in, you should be able to see that that correlates to when k is less than 0 or when k is bigger than 12 over 5. And those there will be the range of values for k at which this is true. Perfect. So that will be the solution to part B there. Right, question 9. So this is a nice bit of trigonometry. I'm a big fan of trigonometry. For trigonometry in year 1, the two things you really solidly need to know are the identities that tan x equals sine over cos, sine x over cos x, and that sine squared x plus cos squared x equals 1. Now, you cannot answer trig questions in year 1 without knowing those facts. And straight away here, I can see that that's going to be what we need to do this question. Okay, so it says, show that the equation 3 cos x plus 3 equals sine x tan x can be written in the form of 4 cos squared x plus 3 cos x equals 1. Alright, so to be able to do this, if we play almost a game of spot the difference, I think can be helpful with this. You can clearly see that the equation that we're starting with here has a tan x in it, and the one that we're trying to turn it into doesn't. So the very first thing that I would do here is I would take the tan x and I'm going to make that substitution from that identity that we just need to know off by heart. Again, if you don't know those identities off by heart, stick them on a flashcard and just make sure that you do as soon as you can. So let's substitute this in then. So then we get left with 3 cos x plus 3 equals sine x tan x. So that's times sine x over cos x. Now straight away here, I can see that I can simplify this. I can rewrite this bit here, sine x times sine x over cos x, as sine squared x over cos x. Remember, that's essentially multiplying fractions together, and if it helps, you could visualise sine x as just being sine x over 1, and so then we're just timesing the tops together and timesing the bottoms together. So we've got this now. Now, looking again at where it needs to be, playing spot the difference again with this equation we're trying to turn it into, I can see two things of note. One is we have a fraction here, and there isn't a fraction on what we want it to be, so it would probably be wise to multiply through by that denominator to stop it being a fraction anymore. And also another difference is that our one has sine squared, but the finished article doesn't. Okay, so those are two things that I'm going to do to try and get it as what they want, just by, again, essentially playing a game of spot the difference. So let's start by multiplying through by that denominator so that we don't have any fractions to play with anymore. So if we times both sides by cos x, we end up getting 3 cos squared x plus 3 cos x equals sine squared x. Okay, so I've just multiplied each of those 3 terms that we have there by cos x. Now we have that little issue of that sine squared x because we don't have that in that final equation that we're trying to make it turn into. So what we need to do is to use this other identity that we have here and rearrange it to get sine squared x as the subject so that we can just make a direct substitution. So rearranging that there, I make it that sine squared is the same as 1 minus cos squared x. So let's rewrite this now on the answer lines and do this final couple of steps that we need to do. So I'm going to replace the sine squared x with 1 minus cos squared x. And now all of the terms that we need are there. There's nothing there that's jarring or that isn't right. All we need to do is to just move everything into the direction that we want. So we want it to be equal to 1. So we'll leave the 1 over there on the right hand side, but we're now going to move over this cos squared x. So we're going to add cos squared x onto each side. And then we get the 4 cos squared x plus 3 cos x equals 1. Done. Perfect. So I hope that made sense. Hopefully you can see that you have to know those identities because without them, you couldn't even begin this question. But perfect, that's really good. Let's try question 10. So here we're given an equation and we're told that it has no real solutions. So no real solutions. And we want to prove that k is bigger than or equal to 0 or less than 2/3. So here, whenever we see that mention of real solutions, in regular maths and not further maths, there's only really one time when the word real comes up. And that again is when we're looking at discriminants. So discriminants give us the information on how many real solutions there are. So if there are no real solutions, then what that tells us is that the discriminant, b squared minus 4ac, is less than 0. So here, what we would need to do is to work out the discriminant of this thing here and then work it out as an inequality. So we want to solve that discriminant. But in this case here, there's an additional thing here. Because if k was just equal to 0, you can see that this wouldn't work, would it? You know, if we had for this particular equation 0 times x squared plus 3 times 0 times x plus 3 over 2 equals 0, that would just become 3 over 2 equals 0, which is wrong. So we could say that there is no real solution because it just doesn't work, does it? When k is equal to 0 as well as working it out for the discriminant. So that's our first little thing. That's why we've got bigger than or equal to 0 here. That's where that's going to come into it. But we've worked that out, we're just going to park that now. But we're going to work out the discriminant. Okay, so b squared minus 4ac is less than 0 because we're looking at where there are no real solutions. So looking at our equation, we could say that a is k, b is 3k, and c is 3 over 2. So let's substitute those in here. So we've got 3k squared minus 4 times k times 3 over 2 is less than 0. So multiplying out those brackets, we get 9k squared minus 6k is less than 0. So here, if we just factorise this now, we will get 3k minus 2 is less than 0. If we work out the critical values quickly here, just by almost parking this for a minute, ignoring the inequality and pretending almost that it is equal to 0, just to work out the critical values, so the points where that curve is going to cross the x-axis, we end up getting that k is equal to 0 and k is equal to 2/3. So if we now take those values, those critical values, and put this onto a nice little curve, which is just a really rough sketch again. So I've put 0, that's one critical value, and 2/3, that's the other one, which are their roots. And then we're being asked here to find where there are no real solutions, which we know relates to when that discriminant, so what we've just sketched there, is less than 0, when those values of that function are negative. And so if we think of negative values, that relates to this, because that is where the curve goes under the y0 line. It's now negative when it's underneath it. So we want to describe the inequality represented by that pink region, and we would say that k is less than 2/3 but bigger than 0. And that is what the discriminant tells us. So finally, if we pair that with what we said here, that k also equaling 0 ends up giving us no solution, then we will just add on and say it's not only is k bigger than 0, but it is also bigger than or equal to 0. And that is how we then end up with our final result for this question. Brilliant, good work. Let's try the next one. This question here wants us to prove from first principles that the derivative of 2x cubed is 6x squared. Now, a lot of people get to these questions and they just think, I know how to differentiate that. That's really easy. How is this 4 marks? And that's the thing. They don't just want us to differentiate that. In our formula booklets, if you were to look in there, you will see that they give us the formula for differentiation by first principles, and that is what we need to use. So it is f-x equals fx plus h minus f of x over h in the limit where h tends to 0, okay? Now that looks very fancy, it looks very technical, but they give it to you, we just need to know how to use it, all right? So the way that I like to structure these is I would just start by saying, okay, f of x is equal to 2x cubed. That is the thing they are asking us to differentiate, so that is our function that we're using. I would then sit down and say, okay, so what is f of x plus h? And that means that we need to replace the x with an x plus h, doesn't it? So now, the tricky bit to this is that we now need to take that and multiply out the brackets. Obviously that's cubic, so it's a little bit harder. We need to sort of take it in some steps. So the first thing that I would do really just to start working that out is I would work out what x plus h squared is. That's going to give us x squared plus 2xh plus h squared. So now that I've got that information, I would work out what x plus h cubed is, because that is going to be x plus h times by what we just worked out x plus h squared is. So we've got to be quite methodical with this. I would just multiply all of the terms by x to begin with, and then all of the terms by h. And then we're going to get a big string here, but that's fine, okay? So that ends up giving us x cubed plus 2x squared h plus xh squared plus, and we're doing the green ones now, x squared h plus 2xh squared plus h cubed. Okay, so that is everything that we have there. We could group together some like terms there, of course. And likewise, if we were feeling brave, we could have just used the binomial expansion to do this as well. That would have been a great way to do this. But if we group together our like terms now, our x squared terms are these. So we end up getting plus 3x squared h. And then likewise, we can do the same thing with our x terms. And you can see we get 3 again. And then just h cubed on the end there. And then of course, if we just write down finally here, f of x plus h, that was 2x plus h cubed, wasn't it? So if we double all of those terms that we have there now, then we would have this sort of complete for that. So we're going to have 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed. Okay, so we've still got some more work to do here, but we've done what I would say is the most difficult bit there. So now that we've done that, we know what f of x is and what f of x plus h is. We can simply substitute this in now to this equation, which is given in our data sheet. Just substitute it in. So we're going to get here that f dash x equals, in the limit where h tends to 0, f of x plus h, so all of that stuff we just said about. And then we subtract f of x, which we said was just equal to 2x cubed. And then it's all over h. So we could see here that the 2x cubed and this 2x cubed are going to cancel out. So that leaves us there with a much simpler bit. So that leaves us with f dash x equals 6x squared h plus 6x h squared plus 2h cubed all over h. If we divide through by h there, we get left with 6x squared. That leaves us with 6x squared plus 6xh plus 2h squared. So we're nearly there now, okay? So this was what we got by simplifying it and dividing each and every one of those terms by h. But finally here, we need to remember that when h tends to 0, that is going to mean that the terms that have an h in them will also tend to 0 because they're being multiplied by a number getting closer and closer and closer to 0. So in that limit where h tends to 0, all that you're left with is 6x squared. And that is why, using the differentiation by first principles formula, the derivative of 2x cubed is 6x squared. And I hope you can see there why this is worth 4 marks. It's a lot more than just thinking, you just times by the power, take 1 away from the power. But this is actually the derivation of differentiation. So, good work. Doesn't come up that often, so people forget it all the time. So make sure that you've got just like an example that you just keep looking at just so you don't forget that it's a thing. All right, so let's try question 12 now. So we're told that given that x minus 3 and x plus 3 are factors of the polynomial y equals 2x cubed plus px squared plus qx minus 9, find the values of p and q. Okay, so this here we want to use the factor theorem. And factor theorem tells us that if we have a factor equal to, say, x minus a, then if we substitute a into the function will equal 0. So in this case, we could say, well, we've got factors being x minus 3 as a factor, so then we could say that if we substitute in 3 into the function, it would end up equaling 0, and likewise, for x plus 3 being the factor, if we substituted in minus 3, then it would equal 0. Now this is really helpful for this question because if we substitute those values in, we will end up getting a pair of equations that in all likelihood we'll be able to solve simultaneously. So let's start over here. Let's start with substituting 3 in. So if we do that, and we go to this original equation, because this is what we're substituting it into, we would end up getting 2 times 3 cubed plus p times 3 squared plus q times 3 minus 9. So we can simplify this now. So 2 times 3 cubed is 2 times 27, so that's 54, plus p times 3 squared, so 9p, plus 3q minus 9 equals 0, okay? Now that is something that we can simplify a little bit. I would do 54 minus the 9, which will give us 45. Plus 45 equals 0, that does the job. You could write that in a few different ways. So long as it's correct and equivalent to what I've got there, then we're good. So now let's have a go at substituting in, using the factor x plus 3, substituting in minus 3 as our little thing to say that it's going to equal 0. So we would get then 2 times minus 3 cubed plus p times minus 3 squared plus q times minus 3 minus 9 equals 0. So that will end up giving us minus 54 plus 9p minus 3q minus 9 equals 0. So that would simplify there to give us 9p minus 3q minus 63 equals 0. So we now have a pair of simultaneous equations. Let's highlight them because there's a lot going on there. We could easily lose track of them, I think, there. So these are the two that we have. So we need to solve these simultaneous equations to solve what p and what q are. So I'm going to write them again up here, and we can have a go at doing just that, okay? So we've got 9p plus 3q plus 45 equals 0, and then we've got 9p minus 3q minus 63 equals 0. So because these two guys have are the same, but they have opposite sign, I'm going to choose to add these two equations together. That's just going to be the way that I do it. Obviously, simultaneous equations, there's a lot of different ways that you can approach it. So just check the final answer I get at the end here and check that you get the same. And if they're the same, then we're good. So we end up getting 18p, and then 45 minus 63 gives us minus 18 equals 0. So solving that, we just get p equals 1. Sounds very reasonable. And then to get q now, we would just substitute that back into one of the previous equations. So let's substitute it back into 1. So sub p equals 1 into equation 1. So we would get there 9 times 1 plus 3q plus 45 equals 0. So there, if we do 45 plus that 9, we end up getting 54. So then we get 3q equals 54 minus 54, and then q there would be minus 54 divided by that 3, and I make that minus 18. So there, at the end of question A there, I have got that p equals 1 and that q is equal to minus 18. So then, for 1 mark at the end here, they want us to work out one other factor of the polynomial. So first things first, I suppose, I would rewrite it using p equals 1 and q equals minus 18. So I'm going to know that I've got 2x cubed plus px squared, so just x squared because p is 1, and then plus qx, which is just going to be minus 18x minus 9. So that would be there, what we have. So now we need to think, what would the other factor be to end up giving us another factor to this polynomial? So here, we know that we have x minus 3 times by x plus 3 times by something, x plus a, and we know that they are equivalent to each other. Now, the easiest thing that I would say is to look at this and think, how can I compare certain coefficients? So I know that if I was multiplying these out together, to make the x cubed value, I would need to be timesing all of the x's together. So x times another value of x there would have to equal 2x squared. Now that tells me that actually this one would have to be a 2x, because otherwise where is that 2 coming from? It would just be x cubed, wouldn't it? So straight away there, that's suggested to us that there must be a factor of 2 in front of the x. So then if we think, okay, how would we get this number that's on its own here, so minus 9? That would be just by multiplying all of just the constants together, the ones without any x's, wouldn't it? So we've already got there minus 3 times something, so that a, and we know that that needs to equal minus 9. Well, minus 3 times 3 is already minus 9, so it would be minus 9a. So to get minus 9 times something, this a, to still equal this minus 9 that we got up here, we know that the a must actually end up being 1. Okay, because minus 3 times 1 does indeed just give us that minus 9 that we're looking for. So that would tell me there that the a would have to equal 1 in that case. So I suppose I would finish up there by saying that that final factor is 2x plus 1. And that would be my final answer. Now, just to say, you could have also alternatively done this by using algebraic division. That would have worked as well, so long as at the end you do indeed get this final factor of 2x plus 1, we're happy. Okay, let's have a look at the next question then. Alright, so here we're told that a curve has the equation y equals 3x squared plus 8x plus 4, and we're told that the point lies on C. Tangent to C at P has a certain equation. Now, whenever we're talking about curves and things like that, quite often differentiation is going to come into this, because curves and tangents, for instance, that's the thing that we're going by on this. We've got a curve and we've got a tangent. Now, what is the link between those two? Well, let's imagine I just mock up what the curve looks like and what the tangent particularly looks like. Let's think, what do those two bits have in common? Well, I guess one is that you know that they have the same coordinate, but then we also know that they have the same gradient. Those are the two things that we know. So at this point P is going to have the same coordinate for both the curve and that equation of a line, but they also have the same gradient. Now if we're told that the tangent to C at P has this equation y equals 2x plus c, we can compare that to y equals mx plus c to actually work out what that gradient is. We could say then that the gradient, which would be m in y equals mx plus c, the gradient of the tangent at that point, and by deduction also the curve at that point, is 2. Now, the thing that links the two of them is that the gradient of a curve is found by doing dy dx, so differentiating. So what we would want to do here is to differentiate this curve, which, remember, to do that, to find dy dx, we take each of those polynomial terms, and if y was equal to, say, ax to the n, so some constant x to the power of n, the differential would be n times by that a, so we multiply through by the power, and then we subtract 1 from the power, okay? So just in case you've forgotten how to differentiate, that is how we do it. We multiply through by the power and then subtract 1 from the power. So if we start there by looking at 3x squared, if we multiply through by that power of 2, we get 6. And then if we subtract 1 from the power, so power of 2 minus 1 just gives us 1. So we just get 2x there. And then plus what the differential of 8x is. 8x, if we multiply through by the power, which would just be 1, we just get left with 8. And then if we take 1 away from the power of 1, we get to the power of 0, which just cancels out. Anything to the power of 0 is just equal to 1. So we just get plus 8. And the final term there, which is plus 4, we just need to remember that constants differentiate to make 0. Okay? So the differential of the curve gives us its gradient. And we've just said, haven't we, that the gradient is equal to 2. So we can equate that to it. So now what we have got, by connecting those two facts, what dy dx is for the curve and the fact that the gradient of the curve at that point is 2, is we have a little equation that we can solve to find out what x is. So this is just straightforward algebra now. Let's subtract 8 from both sides and we get 6x equals minus 6, and then I'll divide through by the 6 to get x on its own, and we get x equals minus 1. So we know then that the x coordinate of P is equal to minus 1. So we're nearly done now. Now what we need to do now is work out what the y coordinate is of P. And to do that, we can either use the equation of the curve or the equation of the tangent, because of course what we said here, both of them have the same set of coordinates, okay? At that point, at that exact point. So if we say then that we know that y equals 3x squared plus 8x plus 4, which is simply the equation of the curve, and we know, don't we, now that x is equal to minus 1, let us substitute that in, because what that will do is that will take the input of x equals 1 and get the output of what the y coordinate is when x is equal to 1. So then we get there 3 minus 8 plus 4, which gives us a y coordinate of minus 1 as well. So we get y equals minus 1. Alright, so I hope there that makes sense to you. So we've got the coordinates of P now, and now we're asked to find out what the value of C is. Now to do this, we know that that relates to the equation of the tangent. We know that y equals 2x plus c. And again, just to remind ourselves, we know that both the curve and that tangent have the same coordinates at point P. So if we were to feed in those coordinates that we've just worked out from part A into part B, we will have the only unknown being c. So we could solve that for c there. So if we substitute that in, so we know that y equals minus 1, and we also know that x is minus 1, we would get minus 1 equals minus 2 plus c. Rearranging that to get c as the subject, we get c equals 1. And that there is the solution for this question. We get that c equals 1. Perfect. So I hope that made sense there. Let us now have a look at the next question. For this question, we're asked to solve 4 cos cubed 2x plus 2 cos squared 2x minus 4 cos 2x minus 2 equals 0. And I think this one's quite a tricky one because it's actually a different topic, but disguised as trigonometry. And of course there will be some trig bits to it, but really overpoweringly, this is actually a factor theorem question. So what I would recommend you do is you start by making a little substitution whereby cos 2 theta is just x, and then just rewrite it, and then just have another look at the question and see what you think of it. So we're being asked here to solve this, and to solve this we're going to need to factorise it, because we can't just rearrange this to get, say, x as the subject. So to do that, what we need to do is to use our factor theorem to do that. First things first though, we don't know any factors at all. So we start simply by making a substitution to try and work out what x could be equal to. Because don't forget, we know that when, say, fa equals 0, then the factor would be x minus a. All right, so let's pull out some numbers, see what we can substitute here to see if we can find a factor. So let's substitute in x equals 1, all right? So if we did that, we would get 4, 1 cubed plus 2, 1 squared minus 4, 1 minus 2. Okay, so that's 4 plus 2 minus 4 minus 2, which does indeed equal 0. So what that tells us then is that a factor of this is x minus 1. So what we can do then is we can use that to work out what the next set of factors are. With the factor theorem questions, once we know what one factor is, one of the ways we can work out the others is by a method called algebraic division. So if we lay this out to do algebraic division to it, so we want to divide 4x cubed plus 2x squared minus 4x minus 2, we want to divide that by x minus 1. So to do that, we say, well, how many x's go into 4x cubed? And that would be 4x squared. The next thing we do now is we multiply the 4x squared by both the x and the minus 1, and we write that underneath, all right? So that's going to be 4x cubed minus 4x squared. And then now what we need to do is subtract those two rows from each other. So 4x cubed minus 4x cubed is just 0. 2x squared minus 4x squared is the same as adding those two things, so we get 6x squared. All right, so now we need to go back to saying how many x's go into now 6x squared. And that is going to be equal to plus 6x, because 6x times x gives us 6x squared, doesn't it? So I would now bring down that minus 4x, and I would now, a bit like we did with the last one, multiply the 6x by the x and by the minus 1, and we're going to write that underneath, okay? So 6x times x gives us 6x squared. 6x times minus 1 gives us minus 6x. So just like before, we want to subtract those two columns from each other. 6x squared minus 6x squared just leaves us with 0. So then we need to do minus 4x minus minus, so plus 6x. And that leaves us with positive 2x, all right? So now, again, we want to ask ourselves, how many x's go into 2x, all right? So x times what makes 2x? And that's going to be equal to plus 2. So bringing this minus 2 down again, what is 2 times by the x times by the minus 1? So 2 times x gives us 2x, 2 times minus 1 gives us minus 2, and if you subtract these from each other, you end up with 0, which is exactly what we wanted. So what that has left us with, and the whole point of why we just did that, is that factor on the top there, that is a quadratic factor, okay? So we can then say that this thing, this 4x cubed plus 2x squared minus 4x minus 2 can be rewritten as the first factor that we found, the x minus 1, but then times by 4x squared plus 6x plus 2. So we've got two factors now, but we want more. We want more factors here, okay? Can we factorise this new bracket that we have just found? So I guess first things first, if I was trying to factorise that, I would take out a factor of 2, and then it's actually 2x squared plus 3x plus 1 that we want to factorise, which can be factorised into 2x plus 1 and then x plus 1. looks great. So all together now, because don't forget there was also this factor here, we could say that we could rewrite this whole thing together as 2x minus 1, 2x plus 1, x plus 1. And that is what it factorises to. And that is equal to 0. So we're not done yet, okay? If we factorised it, we want the solutions now, okay? And the solutions, we're going to get 3 of them. We've got x equals 1, we've got x equals minus 1/2, and we have got x equals minus 1. Still not quite done, because remember, those x's are only there because we put them there, all right? Actually, instead of x equals, remember, x is equal to cos 2 theta. So what we can do now is just rewrite each of those. So instead of x equals 1, we can write cos 2 theta equals 1. Instead of x equals minus 1/2, we can say cos 2 theta equals minus 1/2. And instead of x equals minus 1, we can say cos 2 theta equals minus 1. And each of these, one by one, we can solve, okay? So you can see above that we are told in the question that we want the range of values between 0 and 90. So that narrows it down nicely for us. We shouldn't need to do too much. So first things first is use your calculator to do inverse cos of 1, because we just want 2 theta on its own. An inverse cos of 1 is equal to 0. So either by using the cast diagram or by what I prefer generally, sketching the little cos graph out, if we're looking at when it is equal to 1, there's 2 points at which that happens. There's 0, which was the calculator value that we just got, but there's also 360, okay? So 2 theta could be equal to 0 or 360. So if we were just to rearrange that then, we could say that 2 theta equals 0 or 180 degrees. Now, because we just want values between 0 and 90, we don't need that 180. Let's try the next one then. So cos 2 theta equals minus 1/2. So we need to think, well, what does that equal? And so if we were to do that, for cos 2 theta equals minus 1/2, what we want to do is the inverse of that. So 2 theta equals cos to the minus 1 of minus 1/2. And what we get then is 120 degrees. So again, we can work out other solutions by doing 360 minus 120, which would be 240 degrees. So if we think, well, what is theta then? If that's what 2 theta is, that's going to be 60 degrees or 120. Again, that second solution, the 120, we do not need because we're just looking at solutions between 0 and 90. So we want to eliminate that possibility. So finally here, we've got cos 2 theta equals minus 1. If we do inverse cos of that, we get 2 theta equals 180. Because again, that is exactly where it hits the graph at minus 1, be 180. And so theta there is equal to 90 degrees, which is what we want for the values between 0 and 90. So here in the end, I make it that we have 3 solutions to this. We have got 0, we have got 60, and we have got 90 as our 3 solutions to this question. So an interesting question, this one. It started in a way that maybe you may not think the question was going to go, in that actually, although it looked like trigonometry, it's actually a fact theorem question, but it just shows, don't be blinded by a topic and think, oh, there's cos in it, so it's trigonometry. Of course, it did become trigonometry, but initially you had to use those other tools, basically just algebra, to be able to solve it in the first place. But that's great. Let's have a look at the next question. Okay. So the curve has the equation y equals x squared minus 7x root x plus 13x plus 3. And we're asked to prove that the curve has a maximum point at 415 and fully justify your answer. So to do this, the word that jumps out at me is the word maximum. Because I know that when we're talking about curves, I know that when there's a maximum, I know that dy dx firstly is going to be equal to 0. I know that that is true for a maximum, but I also know that doesn't prove it's a maximum. It's just proving that it's a turning point. So it's proving us that it's something along these lines where the gradient at that point is equal to 0. But if we want to actually determine, is it actually a maximum, what we ideally want to do is to do the double differential. And if that double differential is negative, then what we have is a maximum, okay? So we've established here, just from that keyword of maximum, that what we're going to need to do is to differentiate, equate it to 0 and solve, get that value of x, and then differentiate it again and substitute that value in and determine, is that double differential positive or negative? All right, so let us have a go at this then. So our curve is y equals x squared minus 7x root x plus 13x plus 3. First things first, we need to fix this guy here, okay? Because root x isn't like an actual numerical power. So this is the same. Don't forget that root x is the same as x to the half, okay? So in this case, we've got 7x times x to the half. Now we need to go another step further here, and we need to remember our sort of power rules, that when you times a power and a power, you add those powers together, okay? So by doing that, we'd have x to the power of 1 essentially, add a half, which gives us x to the 3 over 2. So we've got y equals x squared minus 7x to the 3 over 2 plus 13x plus 3. And to differentiate, we know we need to multiply through by the power and then subtract 1 from the power. So dy dx is going to be equal to 2x, because multiply through by 2, and then subtract 1 from the power, minus, and then we're going to do 7 times 3 over 2, and then x to the power of 1/2, because 3 over 2 minus 1 gives us a half, and then plus 13x. Anything that you're differentiating that is just an x term, you can imagine that when we differentiate it, we just get rid of the x term, okay? So it's going to be plus 13, and likewise, whenever you're just differentiating a constant, it just goes away to 0. So what we get left with here is that dy dx is equal to 2x minus 21 over 2, x to the half plus 13. And we know that that is equal to 0 because we're looking at a maximum point. But we're asked to prove that this is the case. And this would be difficult to solve. It's possible to solve this though. We need to think, how could we solve this equation? I would recommend you look at this like a quadratic equation. Okay, so first things first, I would probably get rid of that factor of 2. We know it's equal to 0. So if we multiply everything in this equation through, we would get 4x minus 21 x to the half plus 26 equals 0. So the next thing that I would want to do here is to have a go at factorising this. Now this equation here is actually a quadratic equation, so what we want to do, and you can use a little substitution, maybe you could say that x to the half equals y or something, and then rewrite it as like 4y squared minus 21y plus 26 equals 0. That's 100% valid, and a lot of people like to do it that way if they're not completely confident yet on how to factorise things that aren't just x squared and x and so on. But the way that this would factorise, if we were doing it by factorisation, is you would get 4x to the half minus 13 x to the half minus 2 equals 0. Now what I would say there is you can do that in so many different ways as well. You can use quadratic formula if you prefer that to solve it. I would be more concerned with you just recognising that this is a quadratic equation than you knowing how to solve it, because there's so many tools to do it. Quadratic formula is fail-safe, it will always work so long as you substitute the right things in for A, B and C. Whereas factorising, sometimes for these trickier ones, potentially you wouldn't be a fan of doing it that way, but I'm just advising you, just recognise it's quadratic, and then if you think it's a bit tricky for factorising, just put it in the quadratic formula. So long as you get the solutions correct at the end, then that's all that we care about. So on that note, how could you tell that this one was a quadratic equation? I always go by like the 2-to-1 ratio rule. If the powers of whatever formula you've been given are in a 2-to-1 ratio, it's a quadratic. And of course here we've got 4x to the 1, we could think of that as, and x to the half, and that is indeed in a 2-to-1 ratio, okay? That was a little aside, but it's really valuable to be talked about. So let us now just say what our values for this are. So we're going to have x to the half then equals 13 over 4, and x to the half equals 2. If we then get what x is, we would square both sides to find that, and we would get 169 over 16, And for this one, we would get x equals 4. Now, that's the one that we are excited about because the fact that x equals 4 gives us a turning point is the first little step in what we're being asked to find out. So we know that x equals 4 is going to give us a point on the turning point. Now what we need to do is to think, well, where did that 15 come from? And 15 is the y coordinate when the x coordinate is 4. So to work that out, what we could do is we could go back to that original equation that they've given us and make that substitution of 4 into that. And what we should expect to see is that out will pop our answer. And of course, just use the calculator, make good use of it. So we've got y equals 16 minus 7 times 4, which is 28, times by root 4, which is 2. So that's 28 times by 2, so that's going to be minus 56, plus 13 times 4, so that's going to be 52, plus 3. And if we tap that away in our calculator, we should find that we get the right answer there, which I think is going to give us y equals 15. Perfect. Okay, we're so close now to the end of this because what we have just done by doing that is we have verified that there is certainly a turning point at 4:15, but we don't know for sure if it's the maximum point. And as I mentioned before, to determine if it's a maximum point, we need to work out what that double differential is and work out what the sign of it is at that coordinate. All right? So to do the double differential, let's just return back to what we found dy dx was equal to. And let's differentiate that. And that's going to give us our double differential. So if I differentiate 2x, I know because it's just a single x value, that's going to just become 2. And then to differentiate the next term, so this minus 21 over 2x to the half, I'm going to multiply through by a half and then subtract 1 from the power. So multiplying through by a half there is going to give us minus 21 over 4 x to the power of, and then subtracting 1 leaves me with minus a half. And then plus 13, I know that that number, plus 13, because it's a constant, is going to differentiate just to leave me with 0. So my double differential there is 2 minus 21 over 4 x to the minus a half. So the final thing we need to do is to work out what that value is at that coordinate of 4:15. So when x equals 4, what does the double differential actually equal? And that's going to be 2 minus 21 over 4 times by 4 to the power of minus a half. And your calculator really there can just do the work. You can rewrite that, but the main thing that we want to conclude there is that that is a negative value. And because that is a negative value, we can make a little statement that when the double differential is negative, we have a maximum. And that is all you need to do in that question there. So I hope that that made sense. I hope you can start to see that there's certain key words that's just the trigger for a method. You know, you just need to be able to recognise things like maximum when we're talking about a curve and just know, in all likelihood, this is going to be the pattern that follows next. But let's try out the next question. So for this question here, we're given a beaker of water and we're told that at 100 degrees, the heat switches off and the temperature of that water gets modelled by this equation that they have given us here. So we know that at the beginning, when the time in minutes is 0 minutes, the temperature is 100 degrees and it's only going to get cooler after that. Then we're asked to write down the value of A. So to do this, all we need to do is to substitute in those values, okay? We know that T equals 20 plus A e to the minus KT. Let's substitute in 100 for temperature and 0 for time and see what we get. Now we know that anything to the power of 0 just equals 1, and that's what we have going on there. So we have 100 equals 20 plus A times 1, so just A. So in that case there, A has to be equal to 80. And that will be the solution for part A. So B, explain what the value of 20 represents in this equation. So 20 is going to be basically the absolute lowest temperature that this water is going to go. And that means that if we're given it context, it is going to be what room temperature represents, because this is a beaker sitting in a room and it's never going to go cooler than the temperature of its surroundings. So 20 would actually be the room temperature, or we could say it is like the final temperature of the beaker, because they both mean the same. If you're a bit less physics inclined, you might prefer final temperature, but room temperature would be what that actually represents. They do like us in maths to give context in these modelling type questions, so it's not unusual at all for something like that to come up. Okay, so the next one, when the heat is switched off, the initial rate of decrease of the temperature of the water is 10 degrees per minute. Okay, so a couple of things there. Initial, so that is referring to when the time is 0. They also say the rate of decrease, and anything to do with the rate of change wants us to differentiate, okay? So rate of change, we need to know in A-level maths is a way of asking us to work out the differential, because it's the gradient, essentially, the rate of change. So the way that we work out gradients in maths now is by differentiating, so it's not surprising to us, okay? So what we want to do is to differentiate that initial equation. Let us remind ourselves of it. And also we now know that A is 80, so we do want to use that in this. So we want to differentiate the temperature with respect to time. It would be worthwhile reminding us that when we have something of the form equals kx, the differential is equal to k e to the kx. That's going to be a key fact that we use in this question. So let's differentiate. So we've got 20, that's just a constant. We're taught that constants differentiate just to leave us with 0. And then the next bit is the bit where we can use this rule, okay? So this is going to make minus 80k, because we're going to times by that factor of minus k. So 80 times by minus k is minus 80k, e to the minus kt. Remember, with exponentials, the power doesn't change, okay? They're different to polynomials. So if we look back at the question now, we're told that the initial rate of decrease of the temperature of the water is 10 degrees per minute. So because it's initial, we know that T equals 0. So that is minus 80k e to the 0 basically, which is just minus 80k. We're told that the initial rate of decrease of temperature of the water is 10 degrees per minute. Well, as we know that this is representing just that is the initial rate of decrease, we can equate that to minus 10. Now you might be thinking, well, why is it minus 10? But it's because it's a rate of decrease, and that's like a negative gradient, isn't it? So whereas it's 10, it's decreasing by 10 degrees C per minute, so we write down minus 10. So rearranging that there, we get K equals 1 over 8. So finally there, that is what the answer is, K equals 1 over 8. Perfect. Let's have a look at what the next bit is, because this question continues on the next page. Fact that we use. So here we want to find the time taken for the temperature of the water to drop from 100 degrees to 50 degrees. Now, don't get too confused by that 100 degrees, because don't forget that is just what the starting temperature was. So it's starting from T equals 0, and it's saying at what time is it 50 degrees. So I guess first things first, let's write down our equation again. Let's not forget that we now know what A is, so it's 20 plus 80, e to the, and then of course we know it's minus kt. We know what K is now, so that's minus 1/8 T, okay? So we're asked to say, what is the time taken for it to drop from that initial temperature to 50 degrees? So how long does it take for temperature to equal 50? So they're asking us to solve this equation. And little bit by little bit, I would start by subtracting the 20, and that leaves me with 30 equals 80 e to the minus 1/8 t. And then the next bit will be dividing through by that 80, which will leave me with 3 over 8, or 30 over 80, equals e to the minus 1/8 t. And what the next bit requires is for us to know, how do we get rid of the e? Because we obviously need to get the t on its own, don't we? But how do we get rid of e's so that we can unlock that power? Well, the opposite of an e, don't forget, is ln, so the natural logarithm, ln. So if we take lns of both sides here, we will be able to get rid of that e, which is over on the right hand side, and we just get left with minus 1/8 t. And then finally here, to rearrange this, we could either think of it as dividing through by minus 1/8, or we could multiply through by minus 8. Either are going to give us the same answer, okay? So in this case, we will get t equals minus 8 ln 3/8. And really what we want to do here is just put this into our calculator and see what we get. And I make it 7.85 minutes. They haven't said to give it to the nearest second or anything like that. They just said, what is the time taken? So it's fine to leave this one as a decimal. So that will be our answer. Okay, so for E, it says that we've got a second beaker of water now and it gets heated, but the heat is turned off when the water is at a temperature of less than 100 degrees C. And we're asked to suggest how the equation of the temperature as the water cools would be modified by this. So in our first equation that we've just been talking about, we turned off the heater at 100 degrees, right? So that means it was starting at a higher temperature than it originally was. So if we sort of go back to that original equation. So it started at 100 degrees, we turn it off then, and then that's what it begins with. So if we're now using a lower temperature that we turn it off, what that will mean is that our A would be smaller. Let's think it through. So that initial temperature, remember what we did in an earlier question, when t equals 0, that is the initial, isn't it? And we get t equals 20 plus A. Now, when it was at 100 degrees, we said that A was equal to 80, because 100 t equals 20 plus 80. But if we turn it off at a lower temperature, then A won't need to be as high. For instance, if we turned it off at 80 degrees, say, then we would get like 80 equals 20 plus A, which in this case would be 60. Now, of course, they don't expect us to give specific examples like that. But what we would say here simply is just that A would be smaller. And that would be all we need to say to get our mark for that question. Okay, so nearly at the end of this paper, we're given this one here. So the diagram shows part of the graph y equals 5 cube root of x minus 4 over the cube root of x. And we're told that we have a shaded region enclosed by that curve and the lines x equals 1 and x equals a, and of course also the x-axis as well. So given that the area of the shaded region is 252 square units, find the value of a. So back to those keywords again. Whenever we're given a curve and we're asked to find the area under a curve, area means integrate. Okay, so that's a really important fact that you need to know, because once you know that, again, it's just by the numbers, you know. It's 9 marks here. And even if, for whatever reason, you can't do the later bits of it, if you can still integrate that initial bit, you're going to have some marks. And this is the last question on a paper, so every single mark counts. So first things first, we know that y equals 5, the cube root of x minus 4 over the cube root of x. First things first is I would write those as numerical powers. So we know that cube roots are equal to x to the power of 1/3. So we've got y equals 5x to the 1/3 minus 4 over x to the 1/3. And we also know, don't we, that whenever we have a 1 over x to the power of something, that's the same as x to the power of minus n. So before we even get started on anything, we need to rewrite this so that it has normal numerical powers, no fractions or anything, and so that way we can now integrate this correctly. Now we're told that we want to get the area between 2 points, between A and between 1. Now those are the limits between which we want to integrate. What we want here is to integrate between x is A and 1, 5x to the third minus 4x to the minus 1/3. We want to integrate that with respect to x. So we're going to get a couple of marks now simply for integrating this, and then we'll get more marks for putting the limits in. So integration, just to remind you, if we wanted to integrate something like y equals x to the n, if we integrate that, we will add 1 to the power and then divide through by the power. So that gives us 5x to the 1/3 plus 1, which gives us to the power of 4/3, and then divided by 4/3. So it looks a little bit nasty, but it's fine. We have our calculators to help us. And then minus 4x to the power of, and then minus 1/3 plus 1 gives us to the power of 2/3, and then we divide through by that power of 2/3. And we want to enter in the limits of a and 1. But before we do that, I would certainly simplify these. So if you have 5 and you want to go over 4/3, that leaves you with this 15 over 4. So we've got 15 over 4, x to the power of 4/3 minus, and then 4 over 2/3 would be equal to 6. So we've got 6x to the power of 2/3. So now what we have is the integral, which we need to enter the limits. And an extra thing to add, we know what this integral equals. We know that it is equal to 252 square units, all right? So let's have a go over here and let's do this. Let's put in those limits. So with limits, what you do is you take the top limit and you substitute that in first. And then you put in the bottom limit. So first I substituted in the a's, and now I'm substituting in the 1's. 1 to the power of anything is just always equal to 1. So it's just going to be 15 over 4 times 1, so just 15 over 4, minus the 6. Because again, 6 times 1 to the power of 2/3 is just 6 times 1, which is just 6. And we know that this all equals, because the whole point of integration is it gives you the area, is equal to 252. So let's tidy this up a little bit, I would say. Let us work out what this bracket here is going to give us, because then we can rearrange that. So 15 over 4 minus 6 gives us minus 9 over 4. So at the minute we have 15 over 4, a to the 4/3 minus 6a to the 2/3. And then it would be minus, so plus 9 over 4 equals 252. Okay, so what we have here, you could certainly argue is looking a little bit intimidating, but what this is looking like to me is a quadratic equation. Okay, so no one likes to hear that, but I think it looks like a quadratic equation to me. So for that reason, I would try to tidy this up a little bit, and then I'm probably going to use the quadratic formula. You might be thinking, how on earth am I looking at this, thinking even for a moment, it looks like a quadratic equation, and it is using my 2-to-1 ratio rule of when I look at these powers, I look at them and I can see that those numbers, 4/3 and 2/3, obey a 2-to-1 ratio. And if I've ever got a formula or an equation where the powers are in this 2-to-1 ratio, I know that it is actually like a hidden quadratic equation. So I guess tidying this up, I would first subtract the 252, and then after that I'm probably going to times by 4 just to get rid of that horrible factor of a quarter that I'm not a fan of, because fractions, if we can avoid them, it's just good to get rid of them really. So that leaves me with minus 999 over 4 equals 0. Moving everything on to the left-hand side just so we can get that equal to 0, which we are used to getting when we have a quadratic equation. So now I'm going to times everything through by 4, and then that leaves me with 15 a to the 4/3 minus 6 times 4 is 24, a to the 2/3, and then minus 999 equals 0. Then again, and you really don't need to go this far to be honest, you could divide through by a factor of 3 as well, and that leaves me with 5 a to the 4/3 minus 8 a to the 2/3 minus 3. Now that is not something that I would ask you to factorize. I'm sure that you could, but it's probably going to be quicker at this stage to correctly and accurately use the quadratic formula, okay? So if we're using the quadratic formula, A would be 5, B would be minus 8, and C would be minus 3. So A would then be a to the 2/3. So if we were going to use the quadratic formula, so that would be minus b plus or minus the square root of b squared minus 4ac all over 2a. We would make the substitution of minus 8, so just 8, plus or minus the square root of minus 8 squared minus 4 times 5 times minus 333 all over 2 times 5. We will end up getting there some solutions. So before we write down those solutions, I just want to backtrack a bit and remind you of something special about this equation. Now, we've used the quadratic formula, but of course it's a bit of a funny one, isn't it? It isn't just x squared, x and a number. We've essentially made a little substitution here. So if I write that out, just so you've got it for reference, we've almost imagined that it was 5x squared minus 8x minus 333 equals 0. So if that was the equation, then when we get our solutions here from the quadratic formula, we get two solutions. We get x equals 9 and we get x equals minus 37 over 5. Now, with that, that's fine, that's great, but that isn't what a is. That would have been what x is if it was our traditional quadratic equation. Over here, when we did this, we've essentially made a substitution where x is equal to a to the power of 2/3, all right? So, whereby over here we said that x was equal to 9 and x was equal to minus 37 over 5, instead we could say that a to the power of 2/3 is equal to 9. So if that is the case, we would need to rearrange that to get a on its own now. And we're nearly there. If that is the case, then a would be equal to 27, okay? You would rearrange that by basically square rooting it and cubing it. And that would give us that 27. Now, the other solution, we could do the same thing. We could say a to the power of 2 over 3 equals minus 37 over 5. And we could do the same thing, okay? We could square root that and then cube it. But we'd quickly realise you can't square root a negative number, so that one doesn't provide us with a solution. And therefore, at the end of this question, we could say that the value of a is 27, and that is what will give us that area when we integrate it of 252 square unit. But that's really, really good. I hope that that has made some sense to you and that you're feeling confident that you could repeat that. So really keep an eye out for keywords. Any mention of area in a question like this is likely going to be asking you to do integration. It's not to say 100% there couldn't be some other permutation, but a lot of the time, think to yourself, could this actually be an integration question? But really, really good. Well done for getting through this paper. It's been a big one, and good luck with your revision. See you then. Bye.
Ouch! This is why in some videos I have unexplained scratches.